Okay, now you can start.
Okay. My research is related to aerodynamics. Topic is airfoil aerodynamic performance, prediction using machine learning, and surrogate modeling. Presentation consists of 5 parts. It's introduction, literature review, methods and materials, result and discussion, and conclusion. Introduction consists of 3 small parts. Small little information about airfoil, then machine learning and using the use of machine learning. So airfoil, interest in airfoil shape optimization research is growing because it plays important role in aerodynamic efficiency, defining aerodynamic efficiency. Although real wings have three-dimensional flow, studying airfoils helps understand fundamental aerodynamic properties. Changing airfoil properties allows for inferences about the aerodynamics of a finite wing, including the evaluation of aircraft wings or wind turbine blades. One key performance indicator is the lift to drag ratio, or LDR. It's important metric for aerodynamic evaluation and airfoil optimization. That's it. On the picture, you can see the airfoil. It's a horizontal. It's a plane's wing on the horizontal side, on the 2 dimension. Dark lines, it's airflow. V is velocity of airflow. Angle, it's angle of attack, angle between the direction of airflow and the mm, direction of the airfoil. On the picture, you can see that the head of airfoil directed upward. On the next page, you can see information about what is machine learning and why it is important. Machine learning is algorithm to estimate wind turbine energy production, and it achieved a remarkable 90% accuracy in the predictions. It based on the multi-layer perceptron or MLR. Machine learning also serves as a valuable tool for optimizing unmanned air vehicle-based communication systems and devising UAV trajectory plans that consider factors like power consumption and wireless communication optimization. Uh, However, machine learning plays a much more important role in predicting aerodynamic performance rather than in communication systems and other areas. The last part of introduction is using machine learning. Machine learning and big data analysis and deep learning has been actively explored in recent years. The aerodynamic properties of airfoils play important role in the efficiency of aircraft and turbines because the traditional methods like CFD, it's a computational fluid dynamics, and experimental measurements, they have own drawbacks like high cost and computational time. These disadvantages cannot be underestimated, especially when you work with large volumes or accurate data. The next part of presentation is about literature review. Literature review is about neural network. Here we have 2 types of neural network. It's artificial and convolutional. Artificial neural network surrogate modeling possesses the advantages of computational efficiency and accurate generalization, making it a valuable tool for addressing aerodynamic design challenges. Its applications are aircraft, turbomachines, ring and blade workflow optimization. Meanwhile, convolutional, it's designed for processing images, spatial images, and structured spatial data. It consists of convolutional layers that look at local regions of the data. On the next page, you can see the examples. It's what kind of researches ANN and CNN was used. For example, ANN, artificial neural network, was used during the research of Novuzi and other scientists' research. ANN predicted hydrodynamic performance of hydrofoils. Also, it trained on CFD simulations. During the research of Sirkar, it's other scientist, he used ANN um, to for inverse design of airfoils based on pressure coefficient distribution. Once relate regarding to CNN was used during the research of portal pores. It predicted turbulent flow magnitudes from RANS simulations. CNN outperformed basic network structures, especially in uncertain flows. Convolutional neural network was also used um, by Chen and other scientists' research to predict velocity, pressure fields, and aerodynamic coefficients for airfoils used for airfoils and achieve high accuracy. The next part of presentation is about methods and materials. Here I want to say that important part is about machine learning types. Machine learning has two main types. It's a supervised and unsupervised. Also, in this presentation, I will say about six types of algorithms of machine learning, starting from random forest, gradient boosting, and ending with linear regression. So, methods and materials. In the study, TensorFlow was used to build machine learning models. On the end of the text, you can see the link to TensorFlow. It's open source. The TensorFlow Python library for machine learning has played an important role in constructing models for various machine learning algorithms. The foundation of these machine learning models heavily relies on the quality and diversity of the dataset used for training and evaluation. The dataset employed in this research is a valuable resource acquired from prior study and is openly accessible, as I said, exemplifying the collaborative and open nature of scientific research. As I have mentioned, machine learning has two main types. It's a supervised and unsupervised. Um, the supervised learning its reliance on labeled data, necessitating input data explicitly paired with corresponding target outcomes, enabling the model to discern patterns. In contrast, unsupervised learning harnesses unlabeled data, where the model endeavors to unveil inherent structures or groupings with the data autonomously. On the next, on the following pages, I will say only about algorithms because these three algorithms play the crucial role. The first one types are random forest algorithm and gradient boosting regressor. Random forest algorithm aims to use multiple random trees within a bagging ensemble model. It's a technique that often delivers excellent outcomes across a range of classification problems. For regression, the output is the average of all three predictions. For classification, the final class is determined by majority voting across all trees. Random forest evaluates accuracy and interdependence between individual trees. The algorithm accounts for the overall distribution of errors and reduces them in the final prediction. Each tree makes a prediction using its values. For classification, the final prediction looks like this equation, where x is the test sample, hi is a single decision tree, y is the targeted data, and I is the indicator function that leads to the random forest model of large. It's also the classification outcome of each test tree or the test sample with the maximum number of votes. Regarding to it's the second type, or first it was gradient boosting, and second it's random forest. So gradient boosting, it's several simple models into a single powerful ensemble. Each new weak predictor is added without modifying the previous trees, ensuring robust results. It works stepwise, optimizing any differentiable loss function. The third type of algorithm is adabus prediction, and this type of algorithm is relatively similar to random forest because both of them are tree-based ensemble regressors, but of course they have um, differences. For example, random forest uses bagging while adaboost uses sequential boosting. Random forest In random forest, each tree trained on a random subset data, while in adaboost, each tree corrects errors of the previous one. Um, Also, in a random forest, average ensemble prediction it's the average of all tree predictions, while in adaboost, ensemble prediction is weighted combination of sequential trees. Um, So random forest builds trees independently for diversity, while adaboost builds trees sequentially for error correction. The fourth and fifth types of algorithm is the decision tree and linear regression. Linear regression is a statistical method to model relationship between dependent y and independent x, while decision tree is a non-parametric algorithm for classification and regression. Decision tree models are versatile non-parametric algorithm suitable for both classification and regression tasks. These models tackle these tasks by acquiring straightforward and use rules if then else decision based on the available features. Linear regression is a statistical method, as I said. It employed to establish a connection between the value of dependent variable and independent variables. Its equation looks like this on the picture. Here, x is independent values, and for each value of x, there is a subpopulation of y variables that are homogeneous. M is a slope and A is a intercept. On the presentation, I don't. There is no information about M and A, but it has in the article. Linear regression helps understand how predictors influence outcomes, and it's suitable for simple and interpretable regression tasks. As I said, all all types of algorithms, and after this, it's important to say about implementation of these algorithms. It's important to evaluate the performance to ensure reliable and accurate predictions after developing machine learning models. And to define the effectiveness of these algorithms, we have two equations. It's mean squared error, MSE, and the coefficient of determination. MSE measures the average squared difference between predicted and actual values, while meanwhile the coefficient of determination shows how well the model captures the variability of the data, and values closer to 1 signify a better fit and stronger predictive capability. Using these two metrics allows a comprehensive assessment of the model's ability to predict aerodynamic performance, helping to compare models, algorithms, and guide improvements. The last page of third part of presentation is airflow data. The dataset used in this research was originally compiled in a previous study and is accessible as an open source. This dataset serves as a foundation for implementing an airfoil lift to drag ratio prediction methods using. And on the next page, you can see the five graphs for each algorithms, starting from random forest and ending with linear regression. We can start from first graph. First graph is a random forest. Here, x-axis is a serial number of the observation or sample from the data set from 1 to 1371. Y-axis it's a value of the predicted value normalized between approximately minus 0.895 and 1.105. Blue lines, it's values predicted by the model. In our case, it's values predicted by random forest algorithm. Red lines, it's true values obtained, for example, through CFD, convolutional fluid dynamics calculations. And from the graph A, random forest, we can see that the algorithm predictions are close to the actual values with some small discrepancies, like red ticks, they are higher than blue lines. Graph B, it's a gradient boosting regressor. Its predictions almost match the actual values with very outliers. The model is slightly more accurate than random forest. Graph C is a graph of decision tree regressor. Predictions are noisier, there is more dispersion around the actual values, and the model is less accurate than random forest and gradient boosting regressor. As a result of first three algorithms, random forest, GPR, and decision tree, their results more accurate than the last two, AdaBoost and linear regression. The fourth part of presentation is results and conclusion. The study implemented and evaluated five machine learning models. It's random forest, gradient boosting, decision tree, AdaBoost, and linear regressions. All these models were trained in the Python TensorFlow, as I have mentioned before. The link to TensorFlow on the fifth page, if I'm not mistaken. And it was for predicting lift to drag ratios based on A4 data. The performance of the algorithm was assessed using by two equations. It's MSE, mean square error, and coefficient of determination. The analysis was conducted with various data split ratios from zero point 0.2 to zero point 0.8, which allowed us to test the robustness of the models across different training samples. On the next page, you can see the two tables. First table is accuracy of predicted results for various train test ratios. The second table is performance evaluation metrics of the machine learning algorithms. The comparison plot of actual and predicted values at a ratio of zero point 0.2 clearly demonstrates the high accuracy of math algorithms. Random forest stands out with its predictions most closely matching the actual lift to drag ratio values. From the first table, um, it shows that um, random forest gradient boosting aggressor and the decision tree achieve maximum accuracy here. The first three ones they achieve maximum accuracy at a train ratio of zero point 0.2, while linear regressor achieves this at only zero point 0.3 and Adabus achieves it 0.7. Adabus ranked the bottom position, while Random Forest on the top. From the second table, key observations from the second table, Random Forest and gradient boosting regressor are the most accurate, but they are the slowest train. The training time, here you can see that the training time of Random Forest and GPR, they are the highest. It means that they are the slowest to train, but they are most accurate. Linear regression trains the fastest. It needs 0.33 seconds, and it's also the fastest of all predictions. Adapus expects a long measurement time of 17.35 cents, making it impractical for low accuracy. Decision tree regressor is a compromise, moderate accuracy, and very fast training. Thus, the choice of model directly depends on the goals. For higher accuracy, we can use random forest and gradient boosting regressor. For fast computation, we can use linear regressor and or direction tree regressor. The last part of presentation, it's a conclusion. Significance of this work. This work demonstrates that machine learning models have enormous potential for accelerating the design of airfoils. Machine learning, its algorithms can quickly evaluating airfoil characteristics, minimize the use of expensive CFD, convolutional fluid dynamics, and machine learning can increase the speed of iterations during wing shape optimization. This work demonstrates that machine learning is a powerful tool for predicting aerodynamic efficiency. Uh, as I said, random forest and GPR as the leaders in accuracy, linear regressor is a leader in speed, and type 3 regressor offers a compromise between accuracy and cost. The results confirm that learning approaches can significantly improve the airfoil design process and have great potential for further application. So future work will focus on improving model accuracy and extending these methods to predict flow field properties such as velocity and pressure. And this is the end of presentation. Do you have a question?
Yes, go ahead. Questions?
I have a question, Riza. So, which specific machine learning techniques are implemented in the study, and how those are differ from methods that use AI in practical setting?
Which machine learning? The study uses CNN, convolutional neural network. It was said on the middle of the presentation. CNN, here, convolutional neural network, as uses convolutional neural network as the main machine learning method to process A-fold shapes, and so it explore surrogate modeling techniques such as Gaussian process regression. These methods help create predictive models that are both accurate and efficient.
Thank you for your answer.
Don't forget to write your name, please.
Okay, may I ask question? Yeah.
Yes, go ahead.
Okay, thank you for your presentation, Rizagul. I have a question related to the aerodynamics performance. Which aerodynamics performance metrics are primarily examined and predicted like in the study? And why these particle metrics considered essential for evaluating the overall behavior and the efficiency of airflow design?
You mean what performance metrics are evaluated? The study primarily focuses on predicting lift to drag ratio because this ratio lift to drag plays the most important role in aerodynamics, and lift to drag ratio is an indicator of how efficiently airflow generates lift related to its aerodynamic resistance. So um, the authors analyze in this research analyze lift and drag coefficient separately to ensure that the prediction models understand the underlying aerodynamic behavior. These metrics are essential for assessing how well an airfoil will perform in real world aerodynamic conditions, in real conditions.
Okay, thank you.
Okay, more questions? No more questions?
May I ask?
Yes, go ahead.
Thank you for the presentation. It was so useful. And I want to ask, why does the study choose the represent AFOL, like geometric, in the form of images when training the convolutional neural networks? And what advantage does this image-based representation provide for extraction meaningful geometric and
Efficiency, speed, and scalability. I think. Yeah.
The main advantage of using machine learning instead of traditional methods like CFD is that traditional methods they requires high cost and need more time, while machine learning has advantages like, for example, computational efficiency. While CFD simulations are very accurate, they are also extremely time consuming, as I said, and require resources, high resources, more resources. Machine learning models, once trained, and can provide predictions almost instantly. This makes them ideal for tasks like optimization, rapid design exploration, and real-time aerodynamic analysis. See,
Okay, no more questions? Okay, nice. Okay, thank you very much for your talk. And then we finalize this today. And thank you, Hamid. And the next students will be on next Saturday on the classroom. Okay, on the classroom next week on the classroom. The students who are absent. Okay, so don't forget to send us your the link of the video. Okay.
Okay.
Okay. See you then. See you next Saturday on the classroom. Okay.
Okay, thank you. Bye.
See
Okay,
you. Bye bye.
goodbye.
Bye.
Thank you. Bye.
Goodbye.